Alright, so today we're going to talk about section 2.3, which talks about polynomial functions and their graphs. And first thing, let's define what a polynomial function is. It says let n be a non-negative integer, and let a sub n minus 1, a sub 2, a sub 1, a sub 0 be real numbers, with a sub n not equaling 0. Then the function defined by f of x equals a sub n times x to the n power plus a sub n minus 1 times x to the n minus 1 power plus a sub 2 times x squared plus a sub 1 times x plus a sub 0 is called a polynomial function of degree n. The number a sub n is the coefficient of the variable to the highest power and is called the leading coefficient. Now let me clarify something here before you get all freaked out and everything. You need to understand how these definitions work, because when you go to college there may be some situations where you actually have to teach yourself and you got to actually learn something from this. All this is the math way of defining for every single possible outcome, where you have n being a non-negative integer, which means it's what? If it's non-negative, it's 0 or it's positive. That's it. So understand and put together what all the words mean. And let a sub n minus 1 be real numbers. Now notice where these come in down here in our polynomial. All the a sub n minus 1, they're just the coefficients. They're the numbers in front of your x terms. So we're saying that all the coefficients are real numbers. And a sub n is not equal to 0. The reason a sub n can't equal 0 because we're defining this as an nth degree polynomial. And if a sub n is 0, what happens to that term right there? It goes away. That's why a sub n can't equal 0. So this is a polynomial function of degree n. The number a sub n is the variable is the coefficient of the highest power. It's called the leading coefficient. So don't let all this trip you up. Slow down, look at what it says, and look at where it goes and see what it's actually saying about it. So we know that the non-negative integer, so that's the highest power, is something 0 or positive. And all these numbers here are real numbers. All the coefficients are real numbers. And a sub n can't equal 0. Alright, so here are some polynomial functions over in this column. And these over here are not polynomial functions. And I'll explain why they are in just a second, unless you want to read ahead in the blue. But this is a polynomial function of degree 5. Coefficients -3, coefficient square root of 2, coefficient is 5. Those are all real numbers. Square root of 2 is still a real number, it's just an irrational number. It means it can't be expressed with a decimal that stops. But all those are going to be real numbers, and each one of the powers is non-negative. Alright, over here, same thing when you FOIL this all out. Notice that how you can express it here. This is a degree 6, and I can see that right here because I'm going to have x to the 4th times x times x. That's going to be x to the 6th. And you can see that when you actually multiply it out. But -3 is a real number, -3 is a real number, and 18 is a real number. So real coefficients, x to the 6th, x to the 5th, x to the 4th, all non-negative exponents. Now, let's look over here where we've got some not polynomial functions. Well, -3 times the square root of x. Well, that is a fractional exponent. You cannot have a power that is not an integer. See right here, be a non-negative integer. It must be a whole number. So we've got to worry about it, making sure that it's going to be a whole number. Here, remember, x, the square root of x is the same thing as x to the 1/2 power. Now, the rest of this is fine, but that one term right there messes the whole thing up. All it takes is one single term that does not fit this fit our definition, and the entire thing is not a polynomial. It doesn't have to be all of them. Right down here with g of x, you've got negative 3 over x squared plus the square root of 2x squared plus 5. Well, once again, from here on out, this thing's perfectly fine. Square root of 2, real number. 5, real number. 2, non-negative integer. What we've got here, though, if we wrote that all on one level, we have negative 3x to the negative 2. Negative integer. So we can't have that. Now, what we're going to find when we look at the graphs of these things and get deeper into it, and you can, grab a graphing calculator and check this out, or get online and do some graphing on some of the online graphers you've got, and you can see that when you graph things like this, we get things introduced to the graph that are not real nice. They're points, they're places where we're missing numbers and things like that. Polynomials don't have that. They're nice and smooth curves, and continuous for all real numbers. You get into this stuff over here, you're going to have corners, cusps. Cusps are just curves that make a big sharp corner, and you're going to have parts of the domain that disappear. And here's what we're talking about right there. Smooth rounded corner all the way through, that's the graphs of the polynomial functions. If it has sharp points or missing values, vertical asymptotes, things like that, it's not a polynomial function. Now here are some graphs that are not polynomials. This one we have a discontinuous break. We have a break in the graph right there. Here we have a sharp corner, and a cusp right there. Actually, all these are cusps. But that's what we look at as possibilities when we get into graphs of things that are not polynomials. Polynomials, as we looked at, are nice and smooth and continuous. All right, now, the leading coefficient test tells us what we can expect from our function, from our polynomial, as we get further and further away from the origin. In other words, as we go off to positive infinity to the right and negative infinity to the left, this tells us how the polynomial is going to behave. And it's really, really easy. There are 4 options. 2 for when the degree is odd, and 2 for when the degree is even. You need to know these off the top of your head. These are really easy to do, but you got to spend a little bit of time getting familiar with them, and then once you do, it's kind of a stuck thing. You're never going to forget it. All right, for n equals odd, the way I remember this is for n equals odd, I always think of a base graph that I know. And the base graph that I know that has a degree that's odd is x cubed. And that's basically what x cubed looks like. Well, if you look at x cubed here, you can look at the n behavior to the right and the n behavior to the left, and look here. The n behavior is the same thing. What this is doing, this will tell you what's happening as you get further out here. It tells you nothing about what happens in here. That comes later. All we're talking about right now is what this thing is doing as you get further and further away from the center of the graph, of where this graph's going to be. All right, so if you have n being odd, you want to think of x cubed, y equals x cubed, and if you've got just x cubed, the leading coefficient is positive, you think of x cubed. And x cubed looks like this. So off to the left, we're going down to negative infinity, and off to the right, we're going up to positive infinity. And that's all you're looking for with the leading coefficient test. That's all it tells you, is that as you go off to the left, it's going to fall to negative infinity. As you go off to the right, it's going to grow to positive infinity. Now, what about when the leading coefficient is negative? Well, it's just as easy. You just want to think about when y equals negative x cubed. Well, what does the negative do to the graph? It flips it over. It reflects it across the x-axis. So where you did go off to infinity, negative infinity there, you're now going to go off to positive infinity. And over here where you went off to infinity, you're going to go to negative infinity. So the green line here is negative x cubed, and that is what you need to think of when you have n being odd and the leading coefficient is negative. See? Not real difficult, is it? Now, if you're talking about for n that's even, well, it's even easier because it's a graph that you've seen even more times. And it's just the base even graph that I'll usually think of is y equals x squared. So if the leading coefficient is positive, the graph rises to the left and rises to the right, just like our favorite graph that we just got through talking about in 2.2, the parabola. Now, if your leading coefficient is negative, you're going to do exactly the same thing you did over here. You're going to think about y equals negative x squared, which does what? Flips it across the x-axis again. So we're going to open down. So the graph is going to fall to the left and fall to the right, or go off to negative infinity to the left and negative infinity to the right. So when you've got an even function, they're both going the same direction. And when you're going with have an odd function, they're going in opposite directions. But it's important to know which way is which. So that's why I always remember my x cubed and my x squared. I remember these, and then I always know how to flip them, because the negative is just reflecting it across the x-axis. Now, multiplicity in x-intercepts, if r is a 0, remember a 0 and an x-intercept are the same thing. So if we have a 0 that's algebraically found, graphically it's an x-intercept. If r is a 0 of even multiplicity, that means it occurs an even number of times, then the graph touches the x-axis and turns around at r. It does not pass through the x-axis. If r is a 0 of odd multiplicity, which means it occurs an odd number of times, including 1, then the graph crosses the x-axis at r. Regardless of whether the multiplicity of a 0 is even or odd, graphs tend to flatten out near zeros with multiplicities greater than 1. So for instance, if we had an odd multiplicity that only occurred 1 time and one that had 3 times, it's actually going to be a little flatter around that 0 that occurs 3 times. Now, the intermediate value theorem for polynomial functions says let f be a polynomial function with real coefficients. If f of a and f of b have opposite signs, in other words, one's positive and one's negative, then there is at least one value of c between a and b for which f of c equals 0. Equivalently, the equation f of x equals 0 has at least one real root between a and b. So what we're saying here is this. If we've got a graph, and we don't know what the graph looks like, but let's say we have a here and b here, when we find those function values, there's f of a, we've got a point right there, and then we've got down here f of b, we got a point right there. This one's positive, this one's negative. With a polynomial function, what do we know? It's smooth and continuous. It doesn't have any skips or gaps or places that it doesn't occur. So what do we know? If we go from this point right here to this point right here, we have to do what? We have to cross that axis at least 1 time. Now we may do it more than once. We could do it as simply as a straight line, or we could do it as complicatedly as something like that. Now some of my drawing there looks like it's not a function. Just you get the idea. It can cross that multiple times in between those 2 points, or it can just cross one time. But there is at least one value of c between a and b for which f of c equals 0. And thus we have an x-intercept. Alright, so to graph a polynomial function, yes, we will be graphing these, we're going to use the leading coefficient test to determine the graph's end behavior. We're going to find x-intercepts by setting f of x equal to 0 and solving the resulting polynomial equation. If there's an x-intercept at r as a result of x minus r to the k power, in the complete factorization of f of x, in other words, if we have a multiple 0 case here, if k is even, the graph touches the x-axis at r and turns around. That's the multiplicity of the even multiplicity. And if k is odd, the graph crosses the x-axis at r. That's the odd multiplicity that we just looked at. And if k is greater than 1, then the graph is going to flatten out near that point. All right, then you're going to find the y-intercept by computing f of 0. And then use any symmetry, if you have any, to help draw the graph. Y-axis symmetry, f of negative x equals f of x. Origin symmetry, f of negative x is equal to negative f of x. Those are from even and odd functions. And then use the fact that the maximum number of turning points on the graph is n minus 1. Now that does not mean that there are guaranteed to be that many turning points. That's the maximum number. Alright, so let's do one of these. So in behavior-wise, we're going to look at x to the 4th. And x to the 4th is an even power. And that means we're going to both go in the same direction. And since the coefficient for this is positive, it's going to be up on the left and up on the right. So it's going off to positive infinity over here and positive infinity over there. Alright, so now we need to factor this thing. So to find the x-intercepts, I'm going to let 0 equal x to the 4th minus 2x squared plus 1. Now this is still in a quadratic form, even though my x is to the 4th and x squared. Remember, you can always put in a y. Let's say y equals x squared, and then we would get what? Y squared minus 2y plus 1, easily factorable. Now I'm not going to actually do that. I'm just going to go ahead and graph it. I'm going to have x squared there and x squared over here. Same signs, both minus, minus, minus. Looking for numbers that multiply to give me 1 and add to give me 2. That's going to be 1 and 1. So what do we know here? Well, we know that that's going to factor further, and so will that. They're both differences of squares. So we've got x plus 1, x minus 1 from this first one, and x plus 1, x minus 1 from the second one. Now, here's where we have multiplicities. Notice we have two x plus 1s. So I can write that as x plus 1 quantity squared, and two x minus 1s, so I can write that quantity squared, still equal to 0. And these are going to occur 2 times each. So it has a multiplicity of 2, which means it's going to do what? It's going to come down, hit the x-axis, and go back up. So if we solve this, this is going to be x equals negative 1 from this one and positive 1 from that one. So those are going to be x-intercepts. It is going to actually touch the x-axis. It's just not going to go through. All right, and then we want to find what our y-intercept is. So remember, to find the y-intercept, we let x equal 0. If x equals 0, that goes to 0, that goes to 0, and we have 1. So we have the point 0, 1. Get that point right there. And we can roughly graph this already. Now, it's a good idea to go ahead and plug a couple extra points in there, like 2 and -2. Now, this is an even function, in case you didn't notice this. All the powers of the polynomial are even. Remember, a coefficient's counted as even. So we've got symmetry here that we can take advantage of. So if I were to put in a 2 here, I'm going to have 2 to the 4th minus 2 times 2 squared plus 1. Well, 2 to the 4th is 16. 2 squared is 4 times 2 is 8, and then plus 1. 16 minus 8 is 8. 8 plus 1 is 9. So that means at 2, I'm going to go way, way, way up here already. And by symmetry, I have that same point over here on the other side of the y-axis. So then I can sketch this thing. Remember, it's going to be nice and smooth. Not too smooth, huh? Like I said, your graphs do not have to be perfect, but they do have to carry on everything that needs to be shown. If you draw straight lines and do not make it a nice smooth curve, then I'm going to take points off. It has to be nice and smooth. Can't have just connect the dots with line segments. That doesn't work. That's not how what a parabola looks like or what a polynomial looks like. All right, so that's roughly what we're looking at there. So that is x squared minus 2x squared plus 1. Or sorry, x to the 4th minus 2x squared plus 1. So that's roughly what the graph looks like. And notice, we did keep these pieces of information. It does go off to infinity as we come to the right. It does go off to infinity as we go to the left. So all the pieces of information we brought out were helpful in some way, shape, form, or fashion of drawing this, of sketching this graph. All right, and there's a much better one that I actually let a grapher that I have draw it. All right, so let's graph this one. And we've got x cubed minus 3x squared. Looking at our end behavior, we're looking at x cubed. What do we know about x cubed? Well, a cubic is going to behave like, well, a cubic. And it's a positive exponent, so we know that over here it's going to go down, and over here it's going to go up. So that's the end behavior out away from all those points that we're going to get. That's what the thing's going to do. So now let's look at the actual work and find some key values here. So once again, I'm going to find my x-intercepts. So 0 equals x cubed minus 3x squared. We've got a common x squared we can take out, so let's go ahead and do that. And we're going to have x minus 3. And we've got this thing factored. We have 0 that's going to occur 2 times as a 0. It's a multiplicity 2, and x minus 3 is one factor, so that means that positive 3 is going to occur as a factor 1 time, or as a 0 1 time. So we can plot both these points. 1 right there, because it's a multiplicity 2, remember it's going to be what I call a bounce. It's going to come down and hit it and bounce back up, or it's going to come up from the bottom, hit it and bounce back down. Then we've got another one over here at 3. Now hopefully you can kind of visualize what's going to happen. If I'm coming from the bottom, which goes off to negative infinity over here, and I bounce at 0, it can't cross anywhere else other than these 2 points right here. It can't touch the x-axis anywhere else other than those 2 points right there. So hopefully you can kind of imagine it's going to have to do something like this there at 0, and if it's still down here after the bounce, it's going to have to go through that direction. So you can kind of get an idea of how it's going to deal around the x-axis. But let's go ahead and find some more information. Now, do you need to search for a y-intercept? You can, but do you have to? Well, it's hitting the y-axis right there. So it's not really going to do that much good for you to find the y-intercept, because when you put 0 here and 0 here, you're just going to get 0. 0, 0. Ta-da, there it is. But we don't really have enough information. We only have 2 points. You're going to need at least 3 to 4 points, maybe even 5. And I'm going to get a couple extra by plugging numbers in. So if x equals -1, I'm going to have -1 cubed minus 3 times -1 squared. Well, -1 cubed is -1. Minus 3 times +1 gives me -4. So -1, -4. So right there. When I put in x equals 1, I'm going to have 1 cubed minus 3 times 1 squared. And then that's going to be 1 cubed, which is 1, minus 3, which is going to give me -2. Alright, and I'm going to go ahead and put in 2 while I'm at it. 2 cubed minus 3 times 2 squared. So 2 cubed is 8. 2 squared is 4. And 4 times -3 is 12. That's -4 as well. And then I'm going to go ahead and put in 4. X equals 4. We're going to have 4 cubed minus 3 times 4 squared. So we have 4 cubed, which is 4 times 4, which is 16, times 4, which is 64. 4 squared is 16, times -3 gives -48. And when you do your subtraction there, you're going to end up with 16. Is that right? So over here at -4, we'll just say it's way the crap on up there. So now we can kind of sketch what we're dealing with here. Like I said, it does not have to be pretty. It does not have to be all that accurate, except for where you actually have those points. And its behavior needs to be similar to what the actual graph would be. So that's roughly what we're looking at when we graph this, and we notice that in behavior holds true. We go down here, we go up over here. Alright, and there is an actual real graph of that thing. And notice we held very close to what we did. Alright, let's do one more. And we're looking at this one, and we're in behavioring again, and our in behavior x cubed, an odd, and it's a positive coefficient, so it's going to be the same one, same in behavior that it was before. And that does not mean the graph's going to be the same, but it just means the in behavior is going to be the same. So let's go ahead and look at this. How are we going to factor this thing? We're going to set it equal to 0. Well, we've got 4 terms. One of the big things that you need to remember if you've got 4 terms, one of the things you want to try is by grouping. And if you group here and there, we have a common x squared we can take out here, and we have a common negative we can take out there. So let's see what we end up with when we do that. So we got 0 is equal to x squared times x plus 3. We take out a -1 over here, we're going to get -1 times x plus 3. Remembering these are the common factor that we're factoring out. So we end up with x plus 3 times x squared minus 1 equals 0. So now we can continue factoring this thing. We've got x plus 3, the difference of squares factors to x plus 1, x minus 1. And we can go ahead and plot our zeros there. So we're going to have x is equal to negative 3, negative 1, and positive 1. Negative 3, negative 1, and positive 1. None of these are going to be multiplicities of an even number, so we're going to actually pass through with all of them. We're going to actually draw through, and hopefully you can kind of see how it's going to go. If it's coming from down here, it's going to go up through this one, it's going to turn at some point and come down through this one, and then go back up through that one and take off to infinity, because of what the end behavior tells us. It's going to start over here. This is the only place it can cross for the first time as you're going left to right, and then it's going to have to cross back through there and back through there. So now, there's our x-intercepts. Let's find our y-intercept. If we let x equal 0, that goes away, that goes away, that goes away, and we end up with negative 3. Now, we can find a couple of different values here. I definitely want to try it x equals negative 2. And that means we're going to have negative 2 cubed plus 3 times negative 2 squared minus negative 2 minus 3. So negative 2 to the third power gives me negative 8. Negative 2 squared gives me 4 plus 3, or times 3 gives me 12. Negative negative 2 gives me plus 2 and minus 3. So we have negative 8 plus 12, which is positive 4. Positive 4 plus 2 gives me positive 6. Positive 6 minus 3 gives me positive 3. Point right there. Now, you can use values at negative 4 and negative 2, but I tell you they're going to probably be similar to the ones we've done where they're off the graph. But we know we've got to come from the bottom. We know we're going to get up to that point at least. We may go further, but we know we're going up to that level. We've got to turn there, come back down through our next x-intercept, so that's roughly what our graph's going to look like. Now, like I said, it may do weirder things. It may actually go higher and then come back down. There are different things that these polynomials do because of all these terms in the middle that's attached to the x cubed. But all I want is the basic idea. The big thing I want is you to identify the number of turns, x-intercepts, y-intercepts, and end behavior. If you can get the general shape of this graph, you're fine for the test from this information. Now, you've got to show me this information and how you found it. You can't just draw the graph and say, oh, well, I just knew. No, you didn't just know. Sorry. You're not that person. Now, if you'll notice right here, it actually does go up a little beyond 3, where we drew our maximum value. It actually goes up a little bit above that. If you see that, look real close. And right here, it goes a little bit below our minimum that we had drawn of negative 3. But once again, I'm not that focused on that part. I don't want you to find the minimum and maximum just yet. You'll do that in calculus. I want you to get the basic idea of how to sketch the graph. That's what I'm worried about. All right, so one more thing we're going to talk about is the rational zero theorem. And it says if f of x equals that polynomial definition we had before, has integer coefficients, no square roots of 2 and things like that, so all the coefficients are integers, and p over q, where p over q is reduced to lowest terms, is a rational zero of f, then P is a factor of the constant term a sub 0, and Q is a factor of the leading coefficient a sub n. Now, this kind of comes at you a little backwards, but all this says is that if you have a zero, a rational zero of this polynomial that you're dealing with, let's go ahead and look at this one. If I have a rational zero of this one, it's going to be of the form P over Q, where P is a factor of -6, the last number, and Q is a factor of the leading coefficient 3. Now what that means is we've got to look at all the different factors of -6, or just 6 in general, because we're going to do a plus or minus anyway. So what are all the numbers that are factors of 6? Well, we've got 1, 2, 3, and 6. What are all the factors of 3? 1 and 3. Now we're going to do plus or minus on all these. So now all you do is you look at every single combination you can come up with here. So we've got plus or minus, and I just do one plus or minus in the whole thing. And we're going to have 1 over 1, which is 1, 2 over 1, which is 2, 3 over 1, which is 3, 6 over 1, which is 6, 1 over 3, which is 1/3, 2 over 3, which is 2/3, 3 over 3, which is 1, we already have, and 6 over 3, which is 2, which we already have. So, any rational zero that we have, in other words, any factor that is a zero of this thing, that's a rational number, has to be in this list right here. Must be. It has to be. So if there is a zero that is a real rational number, it's in this list right here. It's plus or minus 1, or plus or minus 2, or plus or minus 3. And what that means is that I've got positive 1, 2, 3, 6, 1/3, and 2/3, and -1, -2, -3, -6, -1/3, and -2/3. So while you're looking here and you're saying, oh, there are only 6, there are actually 12, because there's the positive values and the negative values. But here's the thing. If you're looking at this cold and trying to figure out exactly what numbers you want to try, well, you may look at this and say, oh crap, 12 is a lot of numbers. Yeah, but how many of you narrowed it down from? You had any number, like really any number you can come up with, and now you've narrowed it down to 12. You've done a huge job right here. This makes things so much easier if you have to do it by hand. Otherwise, it's literally trying every single number you can think of. Let's try 4. 4 doesn't fall on this list. It wouldn't work. Let's try 5. 5 doesn't fall on this list. It wouldn't work. So this narrows it down to the ones that if you're going to have a rational zero, it's going to be in this list. So you go from infinity choices to 12. And this is a smaller version. I mean, there are going to be some where you'll have 24 choices. But that's still a huge step down from where you were. Let me see. I'll try any number out of the real number system. Or I'll try one of these 12.